Hey, what's going on YouTube? How are you all? Welcome to my channel. Welcome back to my channel. But if you're new, hello, my name is John. Welcome to the nerdiest frickin' stream here on YouTube. Today we're going to be practicing linear algebra. This is my favorite math subject, TBH. I studied pure mathematics 15, 20 years ago, depending on how you count. How old am I? No. It was like 15 years ago. Like 18 to 15 years ago. I studied this class when I took it freshman year, first semester of college. This converted me from being a chemical engineer and trying to make money as an engineer toward pursuing the life of an artist of math. Like, this to me was eye-opening about how abstract and cool and theoretical and abstract mathematics can be. I had never seen more abstract styles of math, or math for math's sake, until I had taken linear algebra. So this converted me into being a math major, and I still really love it. Then I worked in Silicon Valley as a software engineer for a while. Now I am back trying to relearn mathematics and trying to learn how to teach, but also just studying math for myself because I love it. So welcome. I hope you enjoy this. Please let me know in the comment section what you would like to see out of this live stream. It's very unique. I mean, it is literally a live stream. I will make lots of mistakes here. It's unlike most other math YouTube videos that you'll find. Okay, so we are resetting because recently we got all the way up to a new chapter, Chapter 8. If I can recap what we did last time in Chapter 8, dude, I don't even really remember. I think it was more applications or something like that. More applications of eigenvalues, eigenvectors, primarily. And the way I'm working is that once I get to a new chapter, like Chapter 8, then I'm resetting. And we're going to spend a stream working problems from Chapter 1, and then a stream Chapter 2, stream for Chapter 3. This gives a few different advantages. One is that it gives me spaced repetition. So, like, it takes longer each time until the next time I review this material, but it naturally builds in a rhythm of go back and review the basics. But each time I go back and review the basics, it's getting a notch harder because I'm getting into the more difficult exercises of these sections. So, but it also, it gives me an opportunity to work in a breadth-first way, see a lot of topics, hit some new topics that I hadn't seen the first time that I learned linear algebra. But now, keep everything fresh and work in like this breadth first cycle way, or like a spiral or something. It gives me spaced repetition to review material, but it also gives you all an opportunity to jump into the stream. Like, some people have found me during chapters 5, 6, 7, 8, and I've been like, yo, like, if you want to follow along, like, pause the videos and try to work the problems with yourself. I'm about to restart, and we're going to start Chapter 1 again soon. So, hope you all enjoy it. Let's get into it. Yesterday, actually, I couldn't stream, so, in fact, I did a bonus day. I did a bonus lap through Chapter 1. And here are some of the problems that I worked yesterday privately. We did a problem on vectors in Euclidean space, calculate this vector, u minus 2v plus 4w, and then we did a problem about the norm and the dot product. Then I did privately a problem about matrices and their algebra, then a problem on inverses of square matrices. Then I did a problem on homogeneous system subspaces and bases. Determine whether W is a subspace of Rn. Then we did a problem applying matrices to transition matrices. which are, in other words, Markov chains. So studying the process of Markov chains and finding that this matrix, it was kind of a pain in the butt to do, but eventually we found that it's clear to see that it's a transition matrix, but then it takes some work to see that it is normal, which means that a to the n has no zero entries for some power n. And then another application that I hadn't seen back in college is applications to linear binary codes. So I worked problem 6 privately on my own yesterday. And this has to do with transmission errors. So like if a bit is flipped due to a cosmic ray literally hitting something and flipping a bit from a 0 to 1 or a 1 to 0, can you detect and correct the error message? And this problem was asking how many errors can be allowed before you have to request a retransmission. So in this exercise, I showed on my own that one error transmissions can be corrected, but 2 error transmissions are ambiguous. So all you have to do is find 2 examples. The intended messages are here, 000 and 001. But then if you have 2 errors in the encoded transmission message, then they both map to the same thing. So this vector 000011, you can't decode that without ambiguity, because it could be, the intended message might have been 000 or 001. So all I had to do was just one reminder, one example of an ambiguity. All right, so the problems that we're going to work today are very similar. We're still going to do chapter 1, just this time inviting you all along for the journey. Yo, we got Recuerdos de la Alhambra in the chat. What's up, man? Dude, RDLA, how are you, man? I feel like you haven't made it to too many of the linear algebra streams, dude. It's good to see you. I hope you're doing well. So you tuned in on a good day because we are resetting. I'm starting over. And like, dude, look at this beautiful book. The spine is starting to come apart because we've been practicing so much over here. You know, my name is JC Practices. We're practicing so much that this book is falling apart. Ah, you've been away. No worries, dude. I mean, don't be sorry. Yeah. I'm sorry that you missed it. It's your loss. So, we just did, I did privately problem 9 on my own. Now, Fraleigh and Beauregard 1.1.10. This is a problem about vectors. They say in Euclidean spaces. I'm just going to say in Rn. Same thing. So, this says let U equal 1, 2, 1, 0. 1, 2, 1, 0. V be -2, 0, 1, 6. And W be 3, -5, 1, -2. Compute 3U plus V minus W. Here, how do I want to do this? It says compute this. I'm going to copy it here. I'm also going to say a nice little solution header. Solution 3U minus or plus V minus W is, well, I'm going to go ahead and distribute the 3. 3630 plus negative 2016 minus 3, negative 5, 1, negative 2. I could have distributed the negative and made that a plus, but you know what, same thing. Hey, thanks for getting the answer already. Yeah, I'm doing these more slowly because I want to show the steps along the way. Yo, we got 2 answers in the chat already. Because I want to be teaching this to people who haven't seen it before, but I would have been able to just go, okay, 3, 1, yeah, minus 3, so negative 2. Yeah, you did say negative 2. Okay, I thought I misread that. So you add these together, so 3 minus 2 minus 3 is negative 2. 6 plus 5 is 11. 3, 7, oh wait, no. 3, 4, 3. 0, 6, 8. I think that's what you all said too, right? Negative 2, 11, 3, 8. Did you get it? Yep. All right, cool. So I want to make sure that I'm trying to explain out loud how to do these, but I promise that they will get harder. That's section 1. Section 2, the norm and the dot product. What's up, by the way? She's live. Are you a live streamer also? What's up? She's live. How are you? Fraleigh and Beauregard 1.2.10. No, I did this yesterday, I'm pretty sure. I think I did this one yesterday privately. Let's see. Did I do it? 1.2.10. Yes, I did do 10 yesterday. So I need to cross it out in my book. And today we will do 11. U plus V quantity dot W. So U is negative 1, 3, oops. U is negative 1, 3, 4. V is 2, 1, negative 1. And W is... So these are fairly easy, but over time we are going to get more and more conceptual and more toward proofs. Like this book does have proof and conceptual based problems, but right now they're kind of calculational. Best Friday activity, right? Totally. You're in 12th grade and we've only studied 3D vectors. Can you tell exactly what the fourth vector means? It could be anything. It could be modeling. I don't have examples, but like ChatGPT, for example, this is an extreme example, but ChatGPT is working in matrices of like 2 billion dimensions. Like ChatGPT is calculating 2 billion dimensional vectors, something like that. So it doesn't have to be in the real world. It doesn't have to be physical. It can be data points. Like if you have, these are like the weights of large language models, and like the weights of neurons in a large language model, the weights of neurons in a neural network. It could be, like, let's see, what I'm trying to give good examples. Like if I have an image, I can feed, like, let's say that I have a classifier. I have something called a classifier that will take this image and it will tell me whether I have a dog or a cat. Is the image a dog or a cat, right? So, like, vector 1 might be, does it have a tongue sticking out? If it has a tongue sticking out, maybe it's a little more likely to be a dog. is it knocking shit over, then it's more likely to be a cat, right? If it is sitting on a counter, it's more likely to be a cat. Is it outside? Then it's more likely to be a dog, right? So this is like super hand wavy, but here's a 4-dimensional vector of data points, right? If I give you an image and maybe the image, I feed the image into this classifier and it returns yes, it has a tongue sticking out, no, it's not knocking anything over, no, it's not sitting on a counter, and no, it's not outside. This is probably going to return dog, right? Whereas you get the picture, right? So there's 4 dimensions in this vector, even though it's not in the physical geometry. Even though our geometry is not 4-dimensional, it's still a 4-dimensional list of data. So there's an example for you. I hope that helped. Best Friday activity, right? What's up, Sabina? Thank you. Nah, I don't stream. I made the channel thinking I would be doing lives, but then I didn't get time to create content. What kind of lives would you do? So, I mean, that's just like a random example. There's like way better examples out there, but yeah, 4-dimensional vectors. Oh, here, what about this? Later on, we'll see that polynomials up to degree n create something called a vector space. So something like this, maybe I have, oh wait, I'm trying to use my favorite pattern. Right? Maybe this is one polynomial, and then I have another polynomial that is just x cubed plus 2x or something, right? We can represent the first one. Oh, if we want, well, whatever. You get the point. This is a 5-dimensional polynomial that you can represent with the coefficients 1, 2, 3, 4, 5. And if we wanted to add these two polynomials together, the second one could be written as the vector 0, 1, 0, 2, 0. And if you add those two vectors together, then you get 1, 3, 3, 6, 5. So here's another type of example of 4-dimensional or 5-dimensional vectors. Does that make sense? Like, there's more examples outside of geometry. Like, we're used to thinking of space as vectors, like R3 is space, but R5 it's just a list of numbers, and they can be used for different things. So yeah, we'll see some examples more and more as we go. Cool. And yes, this is the best Friday activity if you're a nerd like me. Like, you all are a bunch of nerds if you're hanging out here on a Friday afternoon. It's a beautiful day outside, and you're watching somebody practice math on the internet. I love it. Okay, now this problem says u plus v dot w is... I'll go ahead and do this here. Solution. U plus V dot W would be, what if we add U and V? We have 1, 4, 3, dot product with W. -2, -1, 3. What is the dot product? You multiply the elements and then add together. 4 times -1 and 3 times 3. So, this is -6 plus 9. So this solution, or this quantity, this new vector is 3. You got it. Yes, yes. Thanks for working the problems with me. It's like way more fun if people are working with me on this. That's awesome. Okay, let's keep moving on. These are going to get tougher. A little bit. Fraleigh and Beauregard. I'm going to cross this out in my book. We did it. Number 11 is done. 1.3 matrices and their algebra. 1.3 point. I'm pretty sure I did number 8 yesterday, so let's do number 9. Thanks for watching. Thanks for hanging out with me. Alright, so we got 1.3.9. We have 2 matrices. A is -2, 1, 3, 4, 0, -1. 4, 0, -1. B is 4, 1, -2, 5, -1, 3. 5, -1, 3. And now it asks what 2a times 5c is. Uh, 2a times 5c is, well, 2 times a. This is also not going to be defined. Is not defined. AB is defined if A is an, what are the letters that they use? MNO? LMN? IJK? What letters would they use? MNO or ABC? LMN, I think. L. I shouldn't say A is A underscore LM. What we need is the number of columns of A. We need the number of columns of A to equal the number of rows of B. So, if I'm very careful here, I'd say A is 2 by 3, so 2A is 2 by 3. B is 2 by 3, so 5. Oh, wait. Oh, C. Oh, shoot. Okay. I wrote down B. Okay. Okay. Sorry. It's true that I was computing this bonus problem, and it's true that this is not defined. B is 2 by 3, so 5B is 2 by 3. And 3 does not equal to 2 or something, if I'm like really being annoying. Okay, but it asked about this other matrix C, which is 2, -1, 0, 6, -3, 2. This is actually the matrix that we want to calculate. And this product will be defined. Solution 2. Um, 2a times 5c is 2 times a is -4, 8, -4, 8, 2, 0, 6, -2, 2, 0, 6, -2. 5 times c, 6, -2. Yeah, all right. 5 times c is 10. I'm looking at this guy. So 10, -5, 0, 30. 10, -5, 0, 30. -15, 10. -15 and 10. And then, now to do matrix multiplication, message retracted. Maybe you caught my error or something. All right, so here we multiply across rows and diagonals, or rows and columns. We take the dot product that we learned in the previous section. So this would be -4 times 10 plus 0 minus, what is that? 30 minus 180? Is that right? 15 times 2 is 30. 30 times... Oh, wait. Yeah, 30 times 3 is 90. I meant to say 90. Is that right? Is there another way? 60 plus 30 is 90, yeah. Okay, so this is -130. -40 minus 90 is -130. And then likewise, I am taking the dot product of the first row and second column. 64 plus 60 is 126. Wait, 64 plus 60 is 124. That's what I'm... Yeah, 164 plus 60 is 124. Now, take the dot product of the second row and first column. 80 plus 30, right, is 110. 80 plus 30 is 110. And finally, we have -8 minus 20, -28. Cool. I feel pretty good that that's correct. It's an odd problem, so I can check. -130, 124, 110, -28. Hey, we got the same answer. Look at that, you got it. So, I'm not even going to check the back of the book. I think that you and I both got it. Thank you for working these problems with me. Number 1.4, solving systems of linear equations. Let's keep going. I've got some food coming, so I will take a break soon. 1.4. Scooch right over. And what problem are we working? I'm pretty sure. Did I do 1.4.9 yesterday? I don't remember doing that one. I skipped 1.4 yesterday. Whoops. I went 1.3 to 1.5. Yeah, I skipped 1.4. Okay. So 1.4.9. It says, describe all solutions. Describe all solutions of a linear system whose corresponding augmented matrix can be row reduced to the given matrix. And it also says, also give the particular solution if asked. In this case, we do have that case. So we have some system of equations that row reduces to this augmented matrix. 0, 1, 1, 3, negative 2, and 0, 0, 0, 0, 0, 0, 0, 0, 0. Yeah. And it asks to find solution with x3 equals 3, x4 equal negative 2. Okay. This is a pretty cool little image, but let's just delete it. We don't need it anymore. Thank you for your question. Alright. I gotta get my burrito soon. So we are going to solve this thing. The second line, this corresponds to x1 plus 2x3 equals 1, x2 plus x3 plus 3x4 equals negative 2. So the free variables are x3 and x4. All solutions are of the form so x1 would be 1 minus 2x3, x2 is negative 2 minus x3 minus 3x4. And then again, we have x3 and x4. Ah, we're running out of space. Let's fix that. So, negative 2 minus x3. So I'm solving for x2 in the second equation up here. And then we have a free variable x3 and another free variable x4. When x3, this is like part A or something. Because this says first describe all solutions and then give the particular solution if requested. When x3 is 3 and x4 is negative 2, (3 and negative 2), so we just substitute. So 1 minus 6 is negative 5. Negative 2 minus 3 is negative 5. Negative 5 plus 6 is 1. And then x3 is 3 and x4 is negative 2. Did you get that? Negative 5, 1, 3, negative 2. Look at you. You're always much faster than me. I gotta catch up with you. You're ahead of me on this. Nice job. Nice job. In your first answer, you have negative 5 minus 3x4, 3x4. But there are two free variables, so you do need x3. You already inserted x3 as 3. But yeah, I see. You just did in two spots. You forgot to put the value of x4, sure. But I think, yeah, this problem does want both of these forms. Because all solutions are like this. But then one solution is, one example is this one. Cool. Let's keep going. We did it. Thank you for working that problem with me. It's more fun when somebody's working them live with me. That's pretty sick. That's awesome. This might be a first, that somebody's like solving all of them with me at the same time. Inverses. Have you seen inverses yet? Fraleigh and Beauregard 1.5.8. Let's get a new color, purple. Let's see. Inverses of square matrices. I'm going to write it down. I'm going to go get my food. I'm going to eat a little bit of food, and we'll keep working this problem. Inverses of square matrices. It says A, find A inverse if it exists. B, express A inverse as a product of elementary matrices if it exists, of course. So our matrix is -1, 2, 1, 2, -3, 5, 1, 0, 12. Be right back. Food. So, food just arrived. I'm going to go get my food real quick. Try this problem if you can. Hey, I'm back. Yo, you got it already. Nice job. Nice job. You got it faster than I expected. Did I lose you? Are you still there? I see 0 viewers right now. I understand if I lost you. Well, I just got my food. I'm gonna eat a little bit of food with you all. Y'all, I hope you're having a good day. Thank you for tuning into my nerdy math video. It's a live stream. You know, sometimes streamers will just eat food on stream. What does the elementary matrix mean? Yeah, good question. So an elementary matrix is a single operation that is... It's an elementary operation. And... elementary operations on matrices are the elementary operations are those such that another elementary operation reverts it back to the inverse. Or not to the inverse, but the identity matrix. I think an elementary operation is such that another elementary operation is its inverse. So, swapping 2 rows, scaling a row, subtracting or adding a multiple of another row to a row. What else? Interchanging, scaling, and then adding and subtracting other rows. You'll see as I work this one. What method did you use? Did you use Kramer's rule or something? It does exist as determinant is 1. You're right. So there are multiple methods to find a inverse. This book is teaching in this section, at least, this method, which I think is computationally efficient. It's more efficient than Cramer's rule. It's, I think, better than Cramer's rule. So you find the augmented matrix, and then you perform a reduced row echelon form. You find reduced row echelon form of this augmented matrix. Yeah, the adjoint of A divided by determinant of A. That works. I think it's not computationally as efficient as this, personally, but I could be wrong. I don't know. You'll see the elementary operations in this process, whereas you don't see them in the way that that you mentioned. So you'll see the individual steps that build the inverse matrix through this problem. So I'm building the augmented matrix that appends the identity on the right, and I'm going to perform row operations. Have you ever learned about reduced row echelon form, like row echelon form and things like that? Yeah, you've learned Cramer's rule. The Cramer's rule for sure is not computationally as efficient as this. It's faster for a computer and for humans to... I'm pretty sure I did this one yesterday, actually. Shoot, I definitely did this one yesterday. It takes a little while. Yeah, I did do this one yesterday. Okay, so I'm not going to work it, but you ended up getting negative 36, negative 24, 13, negative 19, negative 13. Oh, I think it's negative 13 in that middle entry. I could be wrong. 7, 3, 2, negative 1. One of us got this one wrong, I guess. Or at least one of us did. Because you put negative 14. You might be right. But anyways, so you do this augmented matrix, and we do row operations. So what I did here was I added, I replaced the second row with row 2. I added 2 times the first row to the second row. So if you add 2 times the first row to the second, then we get a 0 in this entry, and that was like my target. That was my goal. So then 4 plus negative 3 is 1, 2 plus 5 is 7, 2 plus 0 is 2, and 0 plus 1. That operation of adding 2 times the first row to the second, you can write that operation as this matrix. And then in the next line, what did I do? I added the first row to the third. R3, I like to say R3 prime, like the new row 3 is row 3 plus row 1. And then that is captured by row 3 plus row 1. This is like the add row 1 to row 3 matrix. And then you just keep doing this, and it takes multiple steps. But eventually you row reduce this here, so the identity is on the left, and then whatever is left on the right is the inverse. And then the inverse is the product of all of those individual matrices, all of those individual steps. I just copied them over here. So I already did this problem yesterday. I'm going to write down the next problem and let you think about it while I eat some food. Let me write down the next problem. Fraleigh and Beauregard 1.5.9. Find A inverse if it exists. Where A is... this one's not so bad, I think. 1, 0, 0, 0, 0, 0. Woo! So this is a large matrix, but it's actually not so bad. So we have all the entries are along this diagonal. So you should be able to see what matrix will invert this matrix. So give it a try. Oh, you're solving these while traveling. And, whoa, you don't have paper or notebook? You're doing them in your head? Wait, are you doing these in your head? What? What do you mean? That's not... Don't tell me that. You're gonna make me very sad. I can't do anything like this in my head. I mean, this one I could. This one I could say directly, but the previous problems, like calculating the adjoint of that last matrix you did in your head? I don't believe it. You asked ChatGPT. Pull from Alpha or something. Anybody have an answer with this one? Okay. Oh, you're on a computer. Like, are you on a phone or a computer? I could see that. Like, if you're, like, typing out in, like, in a notepad or something on the computer. Yeah, that's harder than on a phone. Okay. Nice. Good for you. Mm-hmm. Yeah, you're typing it here in YouTube. That makes sense. Okay, that makes sense. Like, yeah, you need to write down some things. It would be hard to do it all directly in your head for these problems. That makes sense. Okay. This problem is slightly computational, but not too much. Like, you could do the or I meant to say slightly conceptual. We could do the exact same process as the previous problem. We could do row reduction. And that would work. That's fine. Nothing wrong with that. Something like a little bit quicker, I think, or cleaner is like we want to multiply this matrix by some other matrix such that they multiply and equal the identity, we can see that we don't need to make any modification to the first row, so we can write the first row, we can keep it the same. The second row, the only thing we need to do is multiply it by -1. If we multiply the second row by -1, then we get a +1 in that second entry, as we want. The third row we need to divide by 2. The fourth row we need to divide by 3. The fifth row we need to divide by 4. And the last row we just need to divide by 5. So this will be an inverse to the matrix. The matrices are getting bigger each week. I mean, kind of. Like, because each time I come back to this chapter, we're working a harder problem, right? We're working a harder problem every time I come back. Yeah, see, you have to think of matrices as performing an operation on an object, on another matrix, usually. So we don't need anything other than scaling. Like, I mentioned those elementary matrices. Like, if the first thing that I did was divide the last... I'm not going to rewrite the whole thing, but 0, 0, 0, 0, 0, 1/5. This would scale the last row by dividing it by 5. You do that, and then you divide the fifth row by 4, and then the next row. Like, you'll see that those multiplied together is this. And you can do the same thing. It's not that hard to do it with the row reduction approach. It's the exact same thing. Alright, we're done with this one. This is one of those good problems that if you try to do it like in an adjoint way, or like taking determinants or something, which the book hasn't defined yet. The book has not defined determinants yet. Like, you can calculate inverses without the determinant, and you should calculate inverses without the determinant. So, what's up, by the way, Zombie Salad? It's good to see you again. 1.6, homogeneous systems, subspaces, and bases. Determine whether W is a subspace. Hey, what's up? Bhargav Ram, how are you? Welcome. Welcome everyone to my stream. Where W is 2x1, 3x2, 4x3, and 5x4, such that xi is in R, and this is a subset, of course, of R4. Is this a subspace? Well, this is scary, John. I don't understand anything. What's up, Gideon? I'm only working linear algebra so far, but today it's chapter 1, some of the basics, vectors and matrices, some of the basics. But later on, we're gonna look and see more interesting, more complex linear algebra stuff about like vector spaces or determinants and eigenvalues, eigenvectors, and stuff like that. What kind of math are you studying? Bhargav Ram, how are you? Yeah, you don't know these topics. Well, I told you, you're going to learn something today. A subset W of a vector space here. Let's do it like this. Here's the definition. We need two properties. For all W1, W2, this is called closure under addition, or closure of vector addition. And then secondly, for all W in W and for all real numbers or scalars, closure of scalar multiplication. So, closure under scalar multiplication. It's not a taco, it's a burrito. It's a burrito. But yeah, what's up, Shori? How are you? It's cool that you're studying for the JEE. I've heard it's very hard. I haven't tried any of those problems. I hear it's pretty tough. Burrito, yeah. Yeah, man. Okay, so, knowing this definition, I wonder if you all can try this problem. Is this space closed? under addition. Gideon is simple. Gideon sees John, Gideon clicks. That's awesome. Dude, it takes skill to eat one of these burritos without making a mess. Alright. I ordered it because I'm trying to stream for you all. I ordered food so I could practice math with you all live. I am more full now. Yes. Okay. So I don't want to mess around with like too many crazy indices. So why don't we do this? Let x and y be in W. Then x equals sum 2x1, 3x2, 4x3, and 5x4. For some scalar numbers, for some scalar real numbers, and y is 2y1, 3y2, 4y3, and 5y4 for some real numbers y1 through y4. Then x plus y, if we add those together, and then factor out the scalar, so you add 3x2 plus 3y2, so if we add two vectors in the subspace, or in the subset, the addition of the two vectors is also in the subset. And then therefore it is closed under addition. Now, next, secondly, let x be in W and r be a real number, then r times x is r times some 2x1, 3x2, 4x3, 5x4. This is not that interesting of a problem. Did I misread something? x1, x2, x3, x4, xi in R4. Yeah, I mean, yeah. Okay. This is just kind of like getting used to the definitions. Nothing crazy here. And maybe being able to write like a clear proof a bit. Like showing that this is sums 2z1, 3... well, we've only used x so far, so we can go to y's for something nicer. So, if you multiply a vector by a scalar, then it also stays in the subset. Therefore, the subset is closed under scalar multiplication, as well as vector addition. Yeah, anything is doable, but it's about exploring the world. Okay. You should check out the Galco and UPSC problems. I haven't heard of those. GAOKO and UPSC problems. I'll take a look. And yes, she's live. You've got a point. Like, why am I practicing problems that I already know how to do? Like, I'm not really learning something new right now, but I am practicing it. I'm reviewing these concepts, and I'm reviewing them every now and then so that I can, like, just make sure I don't forget it. But I'm also practicing by teaching it to you all. Like, I'm getting something out of this by showing these solutions to you all and finding other math geeks who want to learn and, like, practice linear algebra. So the purpose of chapter 1 for me is a little more on that side. I'm not learning that much because I know these problems. But the last two sections will be new for me, actually. Oh, okay, you're telling somebody else. Yikes. Yeah, no fighting in the chat, y'all. Y'all are geeking out about who can work harder problems. Yikes. Yeah, keep it chilly. Keep it chilly, both of you. Math isn't worth fighting about. It's not worth fighting over. Peace and love. I think that there is just a misunderstanding here. Sir, you're right. R very uniquely, just like in textbook, it's written as... Yeah, you have to practice writing your blackboard letters. They're written this way because it's hard to make a bold look good on a blackboard. So this is like a way to simulate bold font on a chalkboard. Yeah, it's how mathematicians write those. Yeah. Keep it chilly. Keep it chilly, everybody. I don't want to time anybody out or anything like that. All right, let's keep going. We solved that problem. I feel good about it. It is indeed a subspace. I don't know if I said that. I didn't complete my thought. Therefore, W is a subspace of R4. Kids these days are show no respect to others. Y'all. I don't want to analyze what happened here, but you both are chill. I like both of you. Don't leave. Just hang out. Enjoy the math. Just enjoy the math. It's fun. Let's all just work our problems together. And yeah, like these. I know that JEE Advanced is super hard, and everybody is always geeking out about how hard it is. Someday I'll work those problems. Yeah, let's just solve these questions. Let's just work these questions together. All right, number 1.7, Fraleigh and Beauregard, 1.7. I think I did number 7 yesterday. Let me make sure about that. Did I do? Yeah, I did do number 7 yesterday. So we're going to work number 8. And this is an application to population distribution problem. We are going to determine whether A is a transition matrix. If it is, determine whether A is normal. What does normal mean? What is a transition matrix? Let's learn. I need to tell you what the matrix actually is. 0, 0, 0, 1, 0. 0, 0, 0, 1, 0. I swear that this is the problem I worked yesterday. I wrote down the wrong one yesterday to work. Yep. I worked the wrong one yesterday. Okay, so I said 1.7.7, but I worked 1.7.8 yesterday. Oops. Okay. Well, I did 8 yesterday, so today let's do 7. I don't think I've done 7 yet. Okay. Yeah, I was like, that sounds familiar. This column that looked like that. Alright, so we have 0, 0.3, 0, 0.7, and 0. 0.5, 0, 0, 0.5, 0. 0.2, 0.1, 0.4, 0.2, 0.1, 0.4, 0.1, 0.2. So, 3, so, yep. 0.2, 0.8, 0, 0, 0, 0.2, 0.8, 0, 0, 0. And finally, 0.1, 0.5, 0.1, 0.5, 0.1, 0.1, 0.2. Okay, so is this a transition matrix? A is a transition matrix. It is. Because 1. All entries Aij are non-negative. Let's clean this up a bit. All entries are non-negative. And then let's clarify, for every entry Aij, it's greater than or equal to 0. That's what non-negative means. Every entry needs to be non-negative. Secondly, all columns sum to 1. For every j equals from 1, oh wait, no. 2, 3, 4. Oh wait, no, from I guess from I equals 1 to 5, Aij, the sum of all entries equals 1 for all columns. For j, this is kind of formal right now, but all of the columns add up to 1 each. So you can think of that like 100% probability. Like every step, like a thing has to have so much probability to transition to another state, or a probability of staying in its current state, and all of those probabilities should add to 1. So I think that's everything we need to call it a Markov chain or a transition matrix. I think that's it. A is likely to be normal. To show here, let's do this. This eraser is too humongous. I like the smaller eraser. I'm pretty sure that this thing is normal. To show A is normal, we show that A to the n has no 0 entries for some n. For some power of the matrix, it has no... the matrix is positive. Every entry is positive. I don't know if there's a clever way to do it, but I'm pretty sure a squared will satisfy the definition. So we could just calculate a squared and be done. It looks to me like a squared will be positive. Okay, dot products of rows and columns. We have 0.3 times 0.5, so this entry is 0.15 plus 0.14. Yep, and that's it. So 0.5 plus 0.14 is 0.29. What's the music in the background? Thank you for asking. I'm glad. Do you like it? Why? Do you like it? Have you ever heard classical guitar before? I'm a big classical guitar fan, dude. I'm a big classical guitar fan. I don't know what song it is because I can't hear it. It plays the music, but I don't know what you hear, even if I put in earbuds. Yeah, it's classical guitar. I'm a huge classical guitar guy. Alright, so this second entry is going to be 0.1. You can play guitar, sir? Yes, actually. Yeah. I didn't want to spoil the surprise, but yeah. Yeah, this is my music, actually. I mean, I didn't write it, but this is my performances. I have another channel. You love the strumming beats. Thanks. Cool. Yeah, that's me. That's me. I have a guitar channel, dude. I'm surprised that you didn't know that by now. You should subscribe. You should subscribe to my classical guitar channel as well. I just practiced guitar over there before coming over here. This math channel is my second channel. My guitar channel is actually bigger. So yeah, I would love to see you there sometime. If I'm not here, I'm probably over there. Oh, I've mentioned it. I mention it periodically. I definitely mention it. That's fun. That's really funny. Okay. So this is super tedious to do, but hey, it's not the worst way to spend some time, I think. The next entry is going to be 0.05. Wait. Yeah, 0.05 plus 0.08 plus 0.02 plus 0.02. So this entry is 0.1, 0.15, 0.17. I think. It looks like you have the Persian white cat. Yeah, she's really cute. She's super cute. She's asleep right now. She's like right here in front of me, sleeping. She's hilarious, dude. She's hilarious. Yeah, I don't like making it seem like as if this channel is only here to promote my guitar channel or something. That's why I don't like to have it up all the time or something. But if somebody asks, like, yeah, it's my that's my guitar channel. So we got 0.25 in the top right entry, 0.25 plus 0.02 plus 0.02 plus 0.02. So 0.06, 0.31. Here we go. Okay. Let's see. Dot product of the second row with the first column is 0.3 times 0, 0 times 0.3, 0.1 times 0, 0.8 times 0.7. 0.8 times 0.7 is 0.56. And then that's it. This is going to be at least 0.15. So it's 0.15 plus 0.40, right? Yeah, 0.55. Man, I don't really feel like doing the entire matrix multiplication right now on stream, because, yeah, that's how the community builds, totally. I show the math on the guitar stream. Sometimes I'm practicing guitar there, and I have the math on the side. And then sometimes here, I have the guitar here, and then, like, hopefully we'll get it to bounce off of each other. Oh, thank you. Yeah, thank you for that. 0.28. We'll pretend as if I'm doing this really, really fast in my head. Yep. There you go. Those are all those numbers. I can see that all these entries are going to become non-zero. So 0 times 0, 0 times 0.3, 0.4 times 0, 0 times 0. Okay, well this one is still 0. So maybe we're not done yet. Right? Third row does contain zeros. Yeah, it contains at least the first one is a 0, right? 0, 0, 0, 0. Yeah, this one is still 0, right? 0, 0, 0.4 times 0.4 is at least 0.16. So because it's 0.16, I'm just going to start saying not 0 or something. Because what matters is whether or not it's 0 or not 0. If anything is positive, like, dude, this is going to be simpler. Let's see. 1, 2, 3, let's do the fourth. So 0, 0. This one is 0. And 0, 0. This one is not 0. Okay? I could say greater than 0, but whatever. This one is not 0. This one is not 0. Because if I find any multiplication of positive numbers, then the rest is going to be at least that number, because every entry is non-negative. So adding further terms is only going to make it bigger, if anything. Yeah, I'm not sure about nilpotent. No, I don't think nilpotent, because doesn't nilpotent mean a to the n equals a? Or does nilpotent mean a to the n equals 0? I forget what nilpotent means. But no, what I'm finding is whether a is a normal Markov chain. A normal nilpotent is 0. Okay, got it. Yeah, normal means that it's every entry is positive. So the opposite, not 0. A to the n equals 0. Okay, got it. Yeah. No, I want the opposite. I want to see that there's no zeros. I want non-zero entries. So, let's see. We're doing 0.7, 0.4. Yeah. Here, we at least have 0.1 times 0.4, so this entry is not 0. And then we have, 0.7 times 0.2, this is not 0. 0.7 times 0.1 at least, so this is not 0. I guess I could use zeros and ones. if I wanted to be like a little more clever and make the definition of how I'm using those. This last one is 0, though, right? Or in this bottom left entry. 0.2, yeah, times 0.0. Yep, that one is 0. 0, 0, 0.2 times 0, 0, 0.2 times 0. This one is still 0. Dude. Okay. This is interesting. It may or may not be normal. It's hard for me to tell right now. So this is not 0. 0.2 times 0.4, and then we have 0, 0. This is still 0. And then this last column is not, this one's not 0. I wonder if there's like a nicer notation or something that I could use. I guess I could use x's, but I don't like implying that they're the same x value everywhere. Cool. Yeah, I forgot about that. Or I don't know if I've ever known that. Involuntary matrix and a nilpotent matrix. That's cool, man. Thank you. Okay. A cubed would be a squared times a. Or I could find a to the fourth by multiplying this matrix by itself. And maybe that's like slightly easier even than looking at two different matrices. Because we just need to find any. The goal is to find any n all entries aij in a to the n are positive. You see what I mean? Yeah, every entry, we want to find every entry is positive. Okay. This thing is going to be something non-zero. What's a good... I'm going to use dots. If it's not 0, I'm going to use a dot. Why not? Dot product of first row and second column is something. Dot product of first row with third column is something, non-zero. First row, fourth column is something. First row, last column is something. Dot product of second row with the first column is something. 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 And now this one, here we start getting into something trickier. Yeah. Do we always keep this structure where this entry is always going to remain 0? We might. It looks like we might. 0, 0, third, the fourth. Yeah, I think it's not normal. 1, 2, third. Yeah, so this one is something. Yeah, and then this is still 0. 0, 0. This one is, yeah, the third entries are both non-zero. 0, 0, not 0. Oh, wait. Yeah, so this is something, because the first entry of the row and first entry of the column are both non-zero. Same for this one. Same for this one. First. Same for this one. And same for this one. And then here, we continue getting the same exact structure. And from now on, it will always be in this form, I think. 0, 0, not 0, 0, 0. Yep. So it doesn't matter what these positive values are. We still maintain this exact same structure, I think. 0, 0, 0, 0, 0. Every future power of this matrix, third entry, this is something. 0, 0, third entry is 0, fourth, 0, fifth. Yep, this is still 0. And then 0, 0, non-zero, this is something else. So, every power of A at least with n greater than or equal to 4 will have this structure. Proof. We don't need to have this structure, or at least we can just show that, I don't know. We show this case for for the third row and first column. Let n be such that a to the n equals A11, A12, A13, A14, A15. I think that this problem does not expect a full proof on this, but A21. So we just need 0, 0, 0, 0, 0, 0 here. A22, A23, A24, A25, A33, A35, A41, A42, A43, A44, A45. And A53, A55. Then, if we square this matrix, has entry, let's call it B. Let's call this the matrix with values B, entries B, such and such. Then B31 is equal to the dot product of 0, 0, A33, oh, and I should say with Aij, all Aij are greater than 0 in this expression. B31 is the dot product of 0, 0, A33, 0, A35, dot product with, and by dot product I'm going to write it as a matrix multiplication with A11, A21, 0, A41, 0. And then that's going to be 0 times A11 plus 0 times A21 plus A33 times 0 plus 0 times A41 plus A35 times 0. And that's 0 plus 0 plus 0 plus 0 plus 0. That's 0. So we can use that. And so you're trying to find primitive matrix, basically. I don't know what a primitive matrix is, but yeah. If A were to be normal, then A to the n then every entry of A to the n is positive, and every higher power if there is some if there were some power such that every entry is non-zero, then every future power of that matrix would also have positive entries, because there's no negative entries. Every entry is non-negative. So because A has non-negative entries. So because we can't find, like, every time that we square a matrix in this form, if you square this matrix and you continue squaring this forever, it stays in this structure. At least this element stays in that structure. I guess we would need to show the same for every element then. What about B32? Well, B32 would also be 0, 0, 0, 0, 0. Yeah. And B34 would be 0, 0, 0, 0, 0. Yep. So, if we squared a to the fourth, then the bottom left entry B51 would be 0, 0, 0, 0, 0. Yep. B52. Let's just check it. 0, 0, 0, 0, 0. And B54. Fifth row, fourth column, 0, 0, 0, 0, 0. Yep. So, because this matrix will remain in this structure, then it will never have non-zero entries in those spots, and it's not normal. So, done. Ooh, I've never heard of Y-lengths bound. Oh, okay. If every element of a to the n is greater than 0, it's called a primitive matrix. Heck yeah. Okay, really. I didn't know that. Thank you. My book has not defined that. Or maybe it did and I didn't see it. But yes, that's exactly. We're trying to show that this matrix is primitive. That's exactly right. And Shori, sleep well, sleep well. Thanks for stopping by. I will say hi to Leo for you. I am not studying anything. I'm studying math for fun because I like it, because it's fun. So, yeah, I am a software engineer. I'm in between jobs at the moment. I'm trying to become a math teacher, actually, y'all. Like, I want to teach high school math, just like simple high school math. I really like math a lot. And yeah. Okay. Cool. So, this next problem is fun. We've got 1.8.7, and this is an application of matrices. Application of matrices to binary linear codes. And this is an optional section in the chapter. I didn't learn this when I took this class a long time ago, so it's really cool to go back and be learning this. Yeah, great work you have going. Appreciate the consistency. Well, thank you. Thank you. I'm glad that you like it. That's really cool, Levi. I didn't know that. So if A is 5 by 5, you only have to go up. You only have to check up to power 16. That's cool. That sounds really interesting. I wonder why. Huh. All right. And is that only true? Is that true for a non-negative matrix, or does the matrix need to be non-negative the way that a transition matrix, like a Markov chain matrix, every entry is non-negative? Or probably, right? I like maths too, but maths doesn't like me back. Yeah, I know the feeling. Yeah, I know that feeling. I think math likes you back, as well as I can tell. As far as I can tell. Okay, so, assuming Okay, so this says, consider the 6-3 linear code C with standard generator matrix one, 1, 0. I'm starting to memorize this. 0, 1, 1. Okay, so what we're doing is we're applying matrices to vectors of matrices to error correcting codes, and we're computing like the Hamming distance of two vectors, being the number of entries that are different. So it says this problem, assuming that the given word has been received, decode it using nearest neighbor decoding using your list of code words in exercise 4. I solved exercise 4 a long time ago. I don't know if I'm going to go back and find it again. Oh my god. Okay, do I have to go back and... I might just have to rework it. I might just rework exercise 4. That's okay. That's okay. We're chilling. I got free time. I got way too much free time. Recall that in the case where more than one code word is at minimum distance from the received word, the code word of minimum distance is selected arbitrarily. So it's saying, in case of tie, we choose a random. Alright, so A. 1, 1, 0, 1, 1, 1. B. 0, 0, 1, 0, 1, 1. C. 1, 1, 1, 0, 1, 1. Let's go over here. D. 1, 0, 1, 0, 1, 0. And E. 1, 0, 0, 1, 0, 1. Okay, in exercise 4, list the code words in C. Okay, so we'll just have to do this, I think. It's not that bad. Solution. First, we list the code words in C. I keep picking the wrong tool. Here it is. So this would be every this would be every input vector to this code. So what does this matrix say? What this matrix says is that if I want to send the message, a binary code message, x1, x2, x3. Instead of sending that, I'm actually going to send x1, x2, x3, x4, x5, x6. So we are adding parity bits. So parity bits tell you if there was an error in the transmission, if there might have been some kind of typo or a cosmic ray like flipped a bit or something, where x4 is x1 plus x2, x5 is x1 plus x3, and x6 is x2 plus x3. And every xi is a Boolean. We're doing Boolean algebra here, like 1 plus 1 equals 0. Yeah, 0 times 1 is 0, etc. 1 times 1 is 1. So to list all the code words, we can run every 3-bit vector through this process, and we can list them like this. Right, 1, 2, 3, 4, 5, 6, 7, 8. That doesn't look right. Why did I double something? Yeah. I repeated this one. There it is. What happened? Why did I do that? Yeah, okay. So now there's 8. 1, 2, 3, 4, 5, 6, 7, 8. Okay, we got it now. So this is going to find every code word in this process. So I'm doing this wrong, aren't I? Wait, something is wrong. No, wait. Does this work? Okay, so 0, 0, 0 times 1, 0, 0 is 0. Yeah, 0, 0, 0. 1, 0. Yeah, 1, 2, 3, 4, 5, 6. This is going to list all of the this is going to list all of the code words in this binary linear code. So I'm doing this matrix multiplication. So here we got 0. This is 0. This one is 1. This is 0. This is 1. And this is 1. This is 0. 1. 0. So on the left, we are multiplying by the identity matrix for the first 3 bits. So it's going to preserve the initial message. It repeats the same first 3 bits. So I'm going to take a shortcut and just copy, because all of these are going to be the same. These bits will all be preserved. then what's interesting are the 4th, 5th, and 6th bits that are added, the parity bits. So that's a shortcut that I'm taking right now. Okay, so now, and it's even easier, I think, to just think of the rules. x4 is x1 plus x2. x1 plus x2 is 1. x5 is x1 plus x3. x1 plus x3 is 0. x2 plus x3 is 1. So I'm just going to follow rule 4 first and find all of these first. So rule 4, x1 plus x2 is 0 plus 1 is 1. 1 plus 0 is 1. 1 plus 0 is 1. 1 plus 1 is 0. 1 plus 1 is 0. Cool. Now, oops. Let's do the same thing, but now this time we're going to do it with the 5th parity bit. So 1st and 3rd bits are 0 plus 1. 0 plus 1 is 1. 1 plus 0 is 0. 1 plus 1 is 0. 1 plus 0 is 1. 1 plus 1 is 0. Cool. Now we can keep going and calculate the 6th parity bit. So the 2nd and 3rd, 1 plus 1 is 0. 0 plus 0 is 0. 0 plus 1 is 1. 1 plus 0 is 1. 1 plus 1 is 0. Cool. So these are code words in C. Then we look up the nearest neighbor for each of these. So do we have 110, 111? 110, 111. I feel that there's a smarter way. Is this where we can do the parity check decoding? Okay, the distance of A to the first code word is more than 1. Yeah, you're shouting 1 plus 1 is 2. 1 plus 1 is not 0. Yeah, that's right. Z2 is 0 and 1, not 1 and 2. But they're equivalent. You can say 1 and 2 or 1 and 0. But most people use 0. What's the best way to do this? Okay. The nearest neighbor to this one is this guy. Nearest is it's definitely just one. It's one bit different. So 110011. Therefore, if we wanted to assume that one bit was flipped, we could decode this as the prefix 110. Like that was the intended message, and there was just one bit that was flipped here to equal that 1. 001 011 is a code word. So the nearest is 001 011. 111 011 has a distance of 2. If I look at the prefix, it has a distance of 2 to this one. So let's see if we can find anything better. If there's something better, then... Aha, I see it. This one. So first I note 111011 is not a code word. So if there's one with one different element, then I can say that that is the nearest that is the nearest entry, because it said that we can pick randomly. So I'm just gonna I randomly picked that one to check. So a nearest code word is 110011. One zero one 010. I don't see any 010s. Like if I look at the suffix and I fix that suffix, there are none that end in 010. So that's interesting. What if I take the middle 101? This isn't really a very scientific way to do this, but 101. I think that this might be the nearest. 101010. So I think that that's the nearest. There's two errors. 001011. There are two differences between these two. And I don't see any that are just one difference. That's enough to say it, right? Like, I see that there's two different bits in these two code word, or in these two words. Right. They're different. They differ by 2. This and this. are flipped. So I can just check throughout and see, are they all, do any of them have one error? Do any of them have one distance 1? Not with the first. The second we've already found is distance 2. The third is at least distance 2. Checking against the fourth, there's at least distance... Oh, wait. It's also distance 2. Right? That's also distance 2, isn't it? Yeah. So we can pick randomly, it said. This problem says that we can pick randomly. Oh, wait. 0, 1, 1, 1, 1. No, that's distance 3. What am I talking about? Was I looking at something else? Oh, yeah. I got this wrong. Yeah, that's distance 3. So by distance, I mean the number of bits that are different. The difference of those, like counting the number. Yeah, this is applied linear algebra. We're applying these binary linear codes, applying to error transmissions. Yo, Mancy, thank you for stopping by. Thank you for saying good luck. I appreciate that very much. Yeah, so this isn't an application that I didn't learn until recently. It is applying to error correcting codes. So like, if you write down some data onto a hard drive, if something went wrong and there was an error while writing that data, your hard drive and your operating system adds a bunch of parity checks. It adds a lot of extra information, like this is all extra parity bits to test to see if there was a typo or like an error, if there was some kind of corruption. If so, then one of these equations would fail. So it's a way to detect errors, like an error in transmission, an error while saving to a database. And you can also think of like when you enter your credit card number into a field and you're buying something, and it can immediately tell that you made a typo in your credit card while typing it. It's because there are similar parity rules testing to see if, the number of even numbers matches the number of odd numbers or something. That would not be the smartest one, but that would be an example. That would be a way to test, or like to find one kind of typo or something. Yeah, so this one also has distance 2. Oh, no. What? 1, 0, 1, 1, 0, 1. This has distance 3. There are 3 bits that are flipped. So that's not as good as the other one that we found. So no, this one is not as well. And the next one is distance 3. And the next one is distance more than 2. Yep, so this is the nearest code word. 101011. Like these are all of the error-free expected received messages if you send a 3-bit message. these are all of the error, like uncorrupted expected transmissions. And it's done by adding these extra bits. X4, X5, X6. We add that to our initial data. We add extra safety data, parity bits. Yeah, I had never learned this until recently, so I'm still learning. 100101. Okay, I see that E100. First, I don't see that in the list. 100101. But this one has one error. The one bit that is different is right here. And I think I saw another one. Yeah, this one is another alternative. There's two options. So 101101. So if we received this message, then we don't know which of the two. We don't know if the original message was 100 or 101. It's ambiguous because they're both only one bit different. That's a little surprising to me, but yeah. I thought that any one bit error could be fixed by this. Huh. I thought that one error could be corrected, but it can't. One error can't be corrected because this one error has two different interpretations. Hey, thank you. You have a nice smile. I appreciate that. Thank you very much. And it was really nice to meet you. I'm actually all done right now. I think we're all done. So these are the nearest neighbors of that entry. So, yo, I think we're done. Thank you, everybody. This is the last section of Chapter 1. It's been a pleasure practicing with you all today. I will say, I have a brand new video that I would love it if you all check it out. Fibonacci for everyone. I think it might be Fibonacci numbers for everyone. New video. I think it was really good. I hope that you all check it out. In this, I went from level 1, which is just simple addition. 2 is medium difficulty, medium addition. All the way up to level 6 and 7. 6 is like, I went all the way up to the eigenvalue, eigenvector proof of fk equals, I should memorize this, 1 over square root of 5, 1 plus root 5 over 2 to the k, and that these are approximately equal. I did the whole proof of that, like a proper pure math proof lecture video on stream live. Lots of mistakes, but we did it, and I think it turned out well. So I hope you all check it out. This is a new video, and I hope you have a great day. Thank you for watching, and thank you for hanging out and practicing linear algebra and math with me. Bye. I gotta go. Bye, everyone. Thanks for watching. Bye.